In this video, we talk about what buckling is and how it occurs in order to calculate what the buckling force would be. So buckling is applying an axial load, like shown here, to some sort of a bar or beam. And in some cases, that axial load, rather than simply shortening, as an axial force does the way we've calculated, can cause this beam to buckle, as shown here, meaning at each value of x, there's some sort of a lateral deflection which is favored in order to shorten the overall length. So this length here and this here are shorter. So it's these lateral deflections due to an axial load, and specifically due to a compressive axial load, that is buckling. Some questions we might ask about buckling is how much force, F, is needed to buckle this column? How does this depend on the way the column is supported? And will this beam actually successfully buckle, can it do this, before it exceeds the ultimate stresses due to an axial load? And in this video, to start answering these questions, we'll derive the buckling force for a column that's supported as shown here by a pin and roller that are a distance L apart, at least prior to buckling. And so we'll ask the question of how does that deflection depend on F? So to do this, we need to relate V of x, the deflection, to the force F that is applied axially across the board. That at this point A, there is a support reaction Fxa that's equal to that axial load F. We can also define, if we make a cut here at a distance x from that point A, we can define the bending moment F of m of x, and then of course the distance of deflection here, little v of x. And we know that capital V of x must be 0 because there was no vertical load here at the point A, and there's no net force on this bar in the vertical direction. We will now sum all the moments around this point A. So we clearly have this, the m of x that we have defined at the cut point, and then we have r cross F here, and that the sum of those must be equal to 0. So we can see though that r cross F, the only contribution in a cross product is that that's perpendicular to the force, which means that distance V of x here. So r cross F is just little v of x times F, and therefore when we solve for m of x, we get the negative of the deflection times the force. If we plug this into the small angle beam equation, we have that the second derivative of the deflection is the moment divided by the flexural rigidity, or minus F over EI times the deflection. So our next job is to solve this small angle beam equation for buckling. So to do this, we'll let K equals the square root of F over EI, this prefactor here, which will turn this equation into the second derivative of the deflection is minus K squared times the deflection. You might be familiar with this solution from a differential equations course, or some quantum chemistry courses. But this has the general solution that the deflection is the sum of a constant times a sinusoid plus a constant times a cosine. And you can see this would be the solution. If you take the derivative of this expression twice, you'll go from the sine to the cosine to the negative sign, and from the cosine to the negative sign to the negative cosine. So because of the ways these differentials work, and that will then maintain the constants, square, we twice take out the prefactor here, and so that ends up with the negative K squared. So we need to, this is a general equation with an infinite number of possible solutions, but we can use the boundary conditions to find the specific solutions to this. So the first boundary condition for a beam on a hinge and a roller is that there is no deflection at either of the endpoints. This means V of 0 is 0, the deflection at the left end is 0, which is C1 times sine of 0 plus C2 cosine of 0. And since sine of 0 is 0, that leaves only C2 times cosine of 0, which is 1. That is just C2, so that tells us C2 is 0, and our equation is now the deflection is C1 times sine of kx. So our second condition is that the deflection at the other end is also 0, which must be C1 times sine of k times L. So this has two solutions, this equation. The first solution is just what we call the trivial solution, that C1 here could be 0. That's one reason that whole thing could be 0. Now in that case, if C1 is 0, then V of x equals C1 times sine of k times x would equal 0. So in this solution, the beam is still straight. It's not buckled. Now this solution is independent of the value of k, which means it's independent of the length. That didn't come into here at all. And also of any force and any flexural rigidity. So this means that you can have a straight beam under any conditions. So watch the video made by my students. Oh, that's a typo. That should be in 2011, the first year I taught this course. And you can find this on YouTube. It's linked on the course web page in the module. But what you'll see is they're standing on a soda can. And if you've ever done this, the soda can, you can, if you're very careful to get on it without creating any lateral perturbation, without pushing sideways in any directions, it can hold your weight. But if you do even the tiniest perturbation, in this case they call it a flick, and they have another person with their thumb just flick the side of the column, it immediately buckles and crunches down into a little disc that you often use to throw the cans away, to recycle them. So why is it then that that same can could buckle or could withstand the force without buckling? It was clearly enough force to cause a buckling, but it could withstand it without buckling. That's because this trivial solution, it could be the only solution at low forces, or it might simply be an unstable solution that's lost upon perturbation in conditions that would otherwise buckle it. That is, you need to somehow create even a tiny little bit of deflection, because these equations require a deflection, and you have to get out of the straight thing into a deflected situation in order to create this buckling. The other solution to C1 sine KL equals 0 is that C1 is non-zero, but instead sine of KL equals 0. So to see how this can be, we know that sine of n times pi is 0 for any integer n. So we could say KL equals n pi, or K is n pi divided by L, just by equating these two. So that is, we have some sort of solutions to this that are non-trivial, or solutions to this at these values of K. But the value K is 0, that is n is 0, that's still the straight solution, because sine of Kx with K equals 0 is still 0 for all x. So still not interested. So what we really want is that buckling solution with, that should be little v of L, is 0 at L, but not in general for all x. So we'll consider first n equals 1, where K equals pi over L, and our solution is v of x is C1 times sine of x over L times pi. And so this is now a solution. And you can see this means that we will have, between 0 and L, we have a half sinusoid there. And the amplitude here at the peak of it is not determined specifically. It's this value C1, and this fulfills this equation for any C1. That is, the buckling is a half sinusoid with arbitrary amplitude C1. If instead we had considered n equals 2 and gotten the equation v of x is C2 sine x over L times 2 pi, well now when we go from x to L, we go through a full 2 pi of the sinusoid. And so what we have is we've reached that 0 point twice, and we have a full sinusoid with an arbitrary amplitude C1. So we see as we increase that n, it's not saying anything about the amplitude. It just says the number of cycles in this buckling environment. So we now want to interpret this to understand the force required for that non-trivial solution, that is the buckling solution. So we see we could have these solutions at various values of n. They result in different numbers of sinusoids between 0 and L. But in all of these cases, k equals the square root of F divided by the flexural rigidity. So that is, the k is a way to represent force. It scales with the square root of force. And plugging in the kappa, this value of kappa, for the equation we had before, we see that the kappa is n pi divided by L, gives us that F is n squared pi squared EI over L squared. So that the smallest f, besides that for the trivial solution where it's 0, is at n equals 1. And so we get buckling at this value with n equals 1. We could also get buckling here. These solutions with higher n's, such as n equals 2, are required when the column is pinned in other places that require having additional sinusoids. So, for example, if it's pinned at L over 2, then you need to have the full sinusoid like this, because you're pinned here and here. If you were pinned at L over 3 and 2L over 3, then you would have 3/2 of a sinusoid. So it still doesn't tell us what happens at other forces. Well, consider this. If we have F greater than the value for the first sinusoid, so let's define this so we can say something simpler. This is called the critical Euler buckling force, in this case for a hinge and a pin. So we call that Fc the Euler buckling force. And now when it's exactly Fc, this beam can take any amplitude of buckling. And so we'll see if we were to apply compressive force and measure the delta L amount of shortening here, so we recognize it's negative, but I'm showing it in a positive direction because I'm defining it as shortening. At first it'll shorten linearly with compressive force due to an axial load. But when it buckles at Fc, it'll now shorten an arbitrary amount as the amplitude goes up and the beam slightly shortens as it goes into that bent form. But when we derived this buckling force, we assumed the small angle beam equation. If in fact the angle becomes larger, if the amplitude exceeds that which can have a good approximation by the small angle, more force is needed. So as we keep going up to higher force, we will eventually go up and it will start to curve upward until eventually you exceed ultimate properties of the beam, the amount that it can compress or stretch on the two sides, or maybe until you curve it all the way around in a circle if it's very long and slender. So we know that at larger forces, it exceeds the small angles, but it still buckles. So it's not that you can say, looking back at the last, that it'll only buckle at these values that are n squared times the Euler buckling force. It buckles anywhere above the Euler buckling force. So this provides both a derivation of the Euler buckling force and an understanding of what buckling means.